This video is an extension to our 8.1 Day 1 lesson. It will answer questions 2, 3, 4, and 5 in full solution. And I'll go fast so we don't waste anyone's time. And you can pause or go slow according to your needs. Question 2. Determine the vector and parametric equation for the line passing through this with a direction of that. So not to be skeptic. If it's passing through 1, 4, that means it arrives at 1, 4. The point 1, 4 could be used as a vector. So we can say that, hey, I have a position vector of 1, 4, which gets me on the line. Is it the only way you can find a position vector? I'm sure there are other ways in different questions. For in this specific one, that is an assumption you can make. And if you're not sure why, there is no real why. It's just you could, and so I did. Please review the previous lesson to get a better grasp of it. Okay? Direction vector, then, is already given to us, -3, 3. I will write my vector equation as I get to the line and I move along the line. There it is. The parametric equation, I break it down into x and y. So the x position of my line would be defined as 1 minus 3t, and the y position of my line would be defined as 4 plus 3t. There is your parametric. Part B. Sketch this line and then determine the coordinates of 4 other points on the line. That's very quick. Well, the sketching portion, just from our previous lesson, shouldn't be hard. I have a vector that goes 1, 4. 1, 2, 3, 4. I get to that line. Oh man, this is going to be a small one. So let's do it bigger. 1, 1, and 1, 2, 3, 4. So that's 1, 4. So I don't want such a large arrow. Okay, that's my position vector. And my direction vector moving along is going to be -3, 3. Oh gosh, so it's going to be -3 and +3 this way. That means it could also be in this way, and so on and so forth, depending on how many parameters that I am going through. Okay, something like that. There's my line. Determine 4 other coordinates. That's basically the same as saying, hey, change the parameters to 4 different ones and tell me where I exist. Like from here, if my parameter is 0, I didn't move anywhere along this line, then the coordinate would just remain as 1, 4. But if I moved along to the right once, it would be, let's see, this is +3 minus 3. That would be +3 would be 4 and -3 would be 1. I would have that, and I just keep moving down. But seeing as how I am just sort of using my head and you have no idea what's going on, let me try to explain. I'm just going to simply say let t equals 0. What does my x become and what does my y become? Use the parameters, right? If that's a 0, x is 1. Sorry. Let's do it this way. My xy coordinate point would be defined as 1 and 4. And that lines up with my position vector because it passes through 1, 4. But what if my parameter was 1? Then my xy coordinate would be defined as 1 minus 3. That's a -2. And 4 plus 3. That is a 7. So this point, -2, 7, belongs on the line. Does that seem to make sense? 1, 2, 1, 2, 3, 4, 5, 6, 7. Somewhere there. It looks pretty accurate. So the t could be, let's do another one, -1. That means my xy would be 1 minus 3 times -1. So 1 plus 3, that's a 4. and 4 minus 3, that's a 1. That's the point I have. 4, 1, 1, 2, 3, 4, 1. Okay, my line isn't the best, but you get the point. Let me try to cheat a little bit. It's a 1, 2, 3, 4, and 1. That's where I'm looking at. Okay, so the t is as anything you want. It just tells me how many times did I go. I could make t equal to 0.5 even. It still gives me an x comma y of, let's see, 1 minus 1.5, negative 0.5, and 4 plus 1.5, that would be 5.5. Okay, it's doable. If this makes sense to you, you should have been able to handle C properly. Does negative 21, 23 exist on the line? In other words, is it possible for x to equal 21? Well, let's try it. If I subtract both sides by 1, I get negative 22 equals negative 3t. Okay, so then t would be, divided negative 3, 22 over 3. Remember, parameters don't change. If the parameter to define negative 21 is 22 over 3, then it's got to be common for both, because that's how we move along the line. The t is a specific number. So if that's the case, well, for y, what is it? 4 plus 3 times 22 over 3. So I'm using this one right here. 4 plus 3t, 4 plus 3t. That would be 4 plus 3 times 3 divided by 3, 22, which gives me 26. That is not 23. Right? Oh, scandalous. Okay, so we know, therefore, Q is not on this line. Do the same thing for negative 29, 34. You're trying to see, hey, how did I get x equals 29? What parameter was used? Subtract both sides by 1. It's a negative 30 equals negative 3t. Divide both sides by negative 3. My parameter must have been a 10. So if my parameter is a 10, that will be 3 times 10 plus 4, 34. Ta-da! I got it. Well, let's pretend I did the calculations. It equals 34. So R is on the line. There you have it. Okay. Lots of interesting things I can do with a vector and parametric equation. Okay. I find this to be more organized, more broken apart, but I still feel that it makes logical sense. See if you can try this again if it was confusing to you. It's a great place to start. Question 3. Determine vector and parametric equations for the line containing points, blah, blah, blah. Okay, so if I have 2 points, you might have noticed, even without me saying anything, if I say, hey, give me a line, you should be able to. Okay, so passing through this and a direction of that, all you need is 2 points to find vectors. So here it is. E, the vector from E to F, is the same as my direction vector. Okay, so let's figure that out. If I finish at F but start at E, that's F minus 6 minus negative 1, that would be a 7. And 11 minus 5, that would be a 6. That's my direction vector. And the points E and F both exist. In other words, I can use this or that as how I get on the line. I can say my position vector is negative 1, 5 or 6, 11, because both vectors will get me on the line that exists, and this direction vector or slope is how I'm going to move. So you choose. I'm going to choose negative 1, 5 just because, arbitrarily. My vector equation is going to be negative 1, 5, and my slope or direction vector times a parameter. The parametric equation would be line, which composes of x being negative 1 plus 7t and my y being 5 plus 6t. That's it. Part B. What are the coordinates of the point where this line crosses the x-axis? Oh, okay. When the line crosses the x-axis, it implies my y value equals a 0. So let's take a look at the parametric equation. Because I have one point or one part of a location, I can calculate the parameter, which will in turn be the same as the x, which allows me to calculate the x. Parametric is so fun. Okay, so once again, 0 is equal to, this is the y value, 5 plus 6t. Subtract 5 from both sides, which gives you a t value of negative 5 over 6. Great. If that's the case, it should carry over into the other part of the parametric equation. I know the numbers aren't pretty, but deal with it. You'll be fine. Okay? Negative 1 minus 35 over 6. So that's 6 over 6. I have negative 41 over 6. So my x-axis, or sorry, my x-intercept is going to be there. What are the coordinates of the points where this line crosses the x-axis? I'm looking for the x-intercept. Done. Part C. Can the equation, blah, 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 also represent the line containing the points E and F? In other words, I want to check, is there a number, a parameter, that will allow me to get negative 1, 5 and get me 6, 11 at the same time? Okay, so let's try it. For this new equation, my parametric equation is going to be x equals negative 15 plus 14 over 3t. My y value is negative 7 plus 4t. And you can, is there a way to make the x value a negative 1? Find your t, plug in your t, and see if that gives me a 5. Is there a t value that can make my x a positive 6? You find your t, you move your t, and see if it makes an 11. Okay. That should be how you solve the question. Another way you could try is by first checking to see if it's even the same direction. Like the first thing you want to do if you want to see if the lines are the same is if they have the same slope, right? So in this case, what you could do is investigate, hey, does this slope or the direction vector and this direction vector operate the same way? Does it go in the same direction? So off on the side, this is a side, you don't have to do it this way. Is the direction vector 7, 6 a scalar multiple of my new equation, which is 14 over 3 comma 4? So let's try it. Let's do the hard numbers, okay? 7 times k has to equal 14 over 3. Is that true? And the same k times 6 has to equal a 4. Well, let's investigate. Dividing both sides by 7, k equals 2 over 3. 6 times 2 over 3 gives me a 4. So they are scalar multiples. That checks out. All right. So if that's the case, let's see if they are in fact coincident. All right. So let me put a little stuff here, little comment here. We are checking to see if the two lines are coincident, literally on top of each other, because that's the question. Can the equation R of this also represent the line? In other words, are they the same line? So if you want to know if they're coincident, well, as I did before, I checked the slopes or the direction vectors. They happen to be the same direction vector. Okay, just scalar multiples. So now I'm going to do my previous strategy and check, hey, are they the same? Okay. For the sake of, yeah, okay, let's do that. Let's see. Because I have this function, I'm going to check with -1. -1 is my x. And 5 is my y. Let's check if they both give me the same t. Adding both sides by 15 gives me 14 equals 14 over 3t. I'm going to multiply both sides by 3, divide both sides by 14, t equals a 3. Add both sides by 7 is a 12, and divide both sides by 4, it's a 3. Ooh, both parameters are the same. So the same parameters got me -1 and 5. We'll do the same thing with 6 and 11. 6 is my x value. And using the same parameter, I need to get 11 as my y value. Add both sides by 15. Multiply both sides by 3, divide both sides by 2. Let's see, divide, multiply 63. What am I doing? That's a 3, and that's a 2, it's a 9. I believe I get a 9 over 2. 3, 2, 9, 2, yeah. Okay, same here. Add both sides by 7, which gives me 18 equals 4t. T is equal to 18 over 4, which is 9 over 2. Okay, they both check out. Therefore, you say, therefore, oops, caps lock. Therefore, the lines are coincident. There it is. We're going to move on. Question 4. Determine a vector equation for the line that is perpendicular to this and passes through the point. Okay, that looked oddly familiar to some of the questions you've done in grade 9, does it not? Perpendicular. Ooh, if my direction vector is -3, 1, 2, 3, 1, 2. It's that. My perpendicular needs to be a certain way as well. But don't get too confused. This represents what? A slope of 2 over -3. A perpendicular slope is +3 over 2. Remember, this bottom number represents the change in x, and the top represents the change in y. Same thing. My perpendicular vector is going to be my change in x and my change in y. Do you see the resemblance? Okay, this is what it looks like when we're talking about negative reciprocals as vectors. I hope that makes sense, that it's not too confusing and it's very logically, it just makes a lot of sense. If not, come talk to me. So my direction vector for my new equation is 2, 3, and it passes through this point. That's another way of saying, hey, I got to 6 at 5 before I started moving in a rate of 2, 3, which means my position vector is 6, 5. And so my vector equation is going to be, I get to 6, 5, and I'm moving at 2, 3 position vector or direction vector. That's it. And of course, I should start doing this for proper true form. You don't know what the t value is, but it could be any real number. That's it. Let's move on. So this question, the purpose of it was to introduce perpendicular. All the skills you've had before, you can still use it. This is what it looks like vector-wise. Question 5. Here's a big one. Consider vector equations are a little different from the usual mx plus b. As long as the direction vector is parallel to the line, a position vector for any point can be used. By that I mean, hey, remember? As long as I get to the line, I don't care what my position vector is. Okay. In short, vector equations can appear completely different, can still be coincident. And the opposite is also true. Even if they look very similar, they could be completely different. Okay, so let's try it. Are the lines represented by the following vector equations coincident? Firstly, you may want to check, hey, do they have the same direction vector? Because if they don't, then right off the bat, we've solved the case. If they are, it's very difficult to just check. It's not easy to check the y-intercept, right? Because this is not limited to the y-intercept anymore. So you might have to do a little bit more. So first, let's type it in. First, let's check if the direction vectors are collinear, in other words, parallel. I don't care what the sizes are as long as they're in the right direction. So, is 2, -1 a scalar multiple of -6, 3, where k, of course, is any real number? Well, that means 2 times k has to equal a -6, and -1 times k has to equal a 3. Well, this seems easier. K has to be a -3, and I'm going to swing that over here. 2 times -3, does it equal -6? Yes, it does. So they are, I'll put a little note now saying same direction vector. So now must check if position vectors get us onto the same line. Okay, so because this is parallel, I'm going to check if 3, 4 exists on this line, or in return, I can say, does -9, 10 exist on that line? Either one will check off, right? Because 3, 4 exists on this line, obviously, but if 3, 4 exists on that line, then they are the same line because they have the same direction vector. Since -9, 10 already exists on this line, we just check that. So choose one. I'm going to choose 3, 4 to test because it's just a smaller number. Not that it really matters. So let's try it. Here's what I'm going to do. In line 1, my x value has to be 3 plus 2s. Right? Right. Okay. And in line 1, my y value has to be 4 minus s. Good? Well, is it possible that I have my -9 and my 10 as my x values? I'm just going to check. And if I have a single parameter that moves my direction vector from 3, 4 to get to -9, 10, then I've proven it. So let's do it. Subtracting both sides by 3, I get -12 equals 2s, and so my s equals a -6. Down here, if I subtract both sides by 4, I get a 6, which means my x equals -6. Okay, they agree. Agrees. Therefore, line 1 and line 2 are coincident. Okay, so it's basically detective work, isn't it? But it's very good exercises for getting used to lines using vectors. At this point, you might be thinking, what about 3D? Why haven't we done anything in 3D? We're not quite ready for that yet. stay tuned for day 2. Okay? Try some others, as I have signed off a lot of textbook questions for you to practice. Get good, and we'll see you on the day 2 video.